Welcome to today's Explainer. We're going to explore a genuinely mind-blowing concept that could, literally, reshape the skyline of our future cities. So when you think of modern construction, you probably picture steel, glass, and of course, endless amounts of concrete. But what if the materials holding our world together didn't actually need to be manufactured in massive, polluting industrial plants? What if the buildings of tomorrow were made out of the dirt right beneath our feet, held together by the exact same everyday food thickeners you might find in your salad dressing or, your ice cream? I know it sounds like complete science fiction, but it's very real, and the data behind it is absolutely fascinating. This brings us right to the core question we're answering today. Can we build strong, structurally sound, modern buildings out of dirt and organic food thickeners? For over a century now, we've kind of operated under this strict assumption that to build high and to build strong, we absolutely have to use cement. But as you're going to see, researchers are actively challenging that assumption, proving that nature might just have a much better, much cleaner blueprint for us to follow. Okay, let's dive into this. Here's our roadmap. First, the Earth building dilemma. Second, biopolymers as the green solution. Third, putting soil to the test. Fourth, strength tests. Fifth, hydrogel bonding. And finally, a sustainable future. Section 1. The Earth building dilemma. The hidden cost of green dirt. Now, humanity has been building with Earth for thousands of years, mainly because it's naturally low carbon. But here is the massive paradox we're facing today. Earthen materials are incredibly eco-friendly for sure, but they are mechanically weak, especially if you're in temperate, wet climates like Northern Europe. To get around this barrier and actually meet modern building codes, builders often kind of cheat. They add up to 8 or 10% cement to the soil to act as a stabilizer and give it that strong bonding. The problem? Well, cement production has an incredibly high carbon footprint. By adding it to the earth, you completely ruin the green credentials of the whole building. We desperately need an alternative stabilizer that provides serious strength without that massive environmental penalty. Moving on to Section 2. Biopolymers, the green solution, are unlikely heroes. This is where a breakthrough alternative could completely revolutionize sustainable architecture. We are talking about biopolymers. So what are they? They're naturally occurring polymers typically derived from plant sources. Traditionally, industries have used them as viscosifiers, which is just a fancy way of saying they thicken liquids. But recently, geotechnical researchers have started exploring them as low-carbon soil stabilizers. When you add them to soil, they've been shown to reduce permeability, increase shear strength, and really enhance durability. They do all this by forming hydrogels when they hydrate, acting a lot like a biological glue. The researchers specifically tested 2 commercially available biopolymers, Guar gum and Xanthan gum. Guar is a neutrally charged polysaccharide, and it forms hydrogen bonds. Xanthan is anionic, meaning it's negatively charged, which allows it to form chemically stronger ionic bonds. Now, what's truly amazing here is that the production of xanthan gum actually consumes carbon dioxide, right? So not only are we avoiding the massive carbon emissions of cement, but we might actually be utilizing a material that takes carbon right out of the atmosphere during its creation. It's a total game changer. Section 3. Putting soil to the test. The 2-7-1 recipe. To really put this to the test, researchers created a base soil mixture, widely known in the industry as the 2-7-1 recipe. That is 70% sharp sand, 20% kaolin clay, and 10% gravel by mass. And this specific blend wasn't just thrown together at random. It complies perfectly with the standard requirements for earthen construction materials. So this gives us our perfect baseline dirt. And here are the actual parameters of the trial. The researchers dry mixed the soil with really tiny amounts of biopolymer. We're talking ranging from just 0.5% to 3.0% by mass. They then added water, compacted the samples into cylinders, and let them air cure in a lab atmosphere for 7 and 28 days. For a direct comparison, they did the exact same thing using a heavy standard dose of 8.0% cement. This sets up a true David versus Goliath scenario in the lab. Tiny amounts of natural gum versus a massive chunk of traditional cement. Section 4. Strength, squished, and pulled. The data drama. Okay, let's look at unconfined compressive strength. Basically what happens when these samples are aggressively squished down. The dashed lines you see represent the baseline strength of those 8% cement samples. Look at what happens with just a tiny 2% addition of guar gum on the left. After 28 days of curing, it actually beats the mighty cement by 35%. And looking at the xanthan gum on the right, after just 7 days, a 2% mix produces a compressive strength that is roughly 50% higher than the cement-stabilized specimens. I mean, this is absolutely shocking. Organic food thickeners at a fraction of the volume are vastly outperforming traditional carbon-heavy cement when compressed. No way, right?
So the crucial point next is how these materials handle being pulled apart. Tensile strength is historically the real weak point of earthen materials. Now, at 7 days, the cement was still stronger. But look at the red line on the right for the xanthan gum at 28 days. As time passed, those xanthan samples actually got stronger, eventually exceeding the cement-treated soil by an impressive 38%. The guar samples, however, actually lost some tensile strength over time. This divergence tells us that the way these two gums chemically bond with the soil is fundamentally different as time goes on. Let's dig into why.
Section 5. How hydrogel bonding works. The microscopic magic. To understand why xanthan gets stronger while guar weakens, we really have to look at total suction and water content. The data confirms that biopolymers create a massive increase in what's called osmotic suction. Basically, the biopolymer hydrogels act like incredibly powerful microscopic sponges. As the soil dries to the laboratory atmosphere, these hydrogels literally pull water and soil particles tightly together. The suction measured in the biopolymer samples was vastly higher than in the unamended soil. This proves that the chemical presence of the hydrogel products is actively sucking the whole matrix together. Let's walk through how this whole transformation happens step by step. First is hydration. When water is added, the biopolymers form those hydrogels. Second is desiccation. As the material cures and dries out in the air, the hydrogels physically transform from an elastic, rubbery state into a hard, glassy state. This is exactly why stiffness and compressive strength shoot up over time. Finally, aggregation. The chemical bonds lock it all together. Now, remember how guar got weaker? Guar relies purely on hydrogen bonds, which are chemically weaker. That explains why its tensile strength dropped off at 28 days once that rubbery hydrogel turned glassy. But xanthan gum is anionic. It actively interacts with the actual cations in the clay portion of the soil to form chemically stronger ionic bonds. This incredible combination of ionic bonding and that glassy hydrogel transformation is exactly why xanthan gum's tensile strength just keeps climbing over time. Section 6. A sustainable construction future. Rethinking our buildings. You know, this isn't just some neat chemistry experiment. As the researchers directly conclude, and I'll read this right from the study, significant improvements to the mechanical properties of soil-based construction materials can be obtained using guar and xanthan gum biopolymers as stabilizers. What this ultimately tells us is that the trade-off we've accepted for decades, sacrificing our green credentials for mechanical safety, is a completely false choice. We don't have to poison the environment with cement just to keep a dirt wall standing. Nature has already provided the structural glues we need. And this brilliantly illustrates the path forward, leaving us with this final, really provocative question. Will the eco-friendly skyscraper of tomorrow be held together by the exact same ingredients found in your food? The data strongly suggests that it's not only possible, but it might actually be mechanically superior. By leveraging the microscopic magic of biopolymers, we can finally unlock the true potential of raw earth construction, lowering our global carbon footprint one completely natural, glassy hydrogel bond at a time. Thanks so much for joining me for this explainer, and I really hope you never look at the dirt outside or your salad dressing the exact same way ever again.